I started using ASAP in 2004 for my PhD work in cataract imaging and analysis. And since then, I've been working to develop eye models in ASAP as a biomedical application. So today we're going to show you that modeling system and also combine it with typical optical mechanical systems that ASAP is used for. All right, we now introduce AHEM, the Advanced Human Eye Model, which is available for ASAP. And its function is to allow the user to generate eye models representing various stages of the eye and any other type of optics associated with the eye. So right now we're looking at a graphic of a basic eye model, and I'm going to take you through some of the simple steps in generating this graphic and the default eye model. All right, so it's very simple to start AHEM. We right-click in our workspace and start Auto Run. And we get a prompt screen. It's a launch screen. And it asks us three questions: a settings, default, or saved file. So right now I'm going to run the default model, but I do have the options for reloading settings that were generated before. If you've been working on an eye model and you just want to reload it. And then also if you have a saved file from some previous session that you want to load. So right now we're going to need default, hit 1. And now it asks me, do I want to save to a file? Well, if I save to a file called settings, then I can do iterations without retyping the word settings. I can also save to a named file, which I can reload later. I'm just going to hit OK and let it run in settings. So the first screen I get is a basic input screen, and it describes most of the factors involved in generating my model. So I can have one or two eyes. I can use a coherent or incoherent source. Right now we're going to use an incoherent one, so it's unchecked. I can choose a monochromatic wavelength, 589 microns, or I can use 4 polychromatic wavelengths, so I'm going to stick with one wavelength for now. Here I have an eye lens model choice. So I have a choice of either simple biconvex equivalent index lens that's controlled by power. I can have a gradient index lens, which is a complex shelled gradient index lens. I can insert an intraocular lens, an IOL, or I can use the Arizona eye model. So I'm going to choose that. I can also put correction on this eye if I wish. I can have axial ametropia, which means I can stretch or compress the eye. Anterior cornea Zernike pupil diameter means if I want to deform the cornea with a Zernike surface, I can do that. I can control the iris or pupil diameter. I can put targets at a certain distance away from the eye, and also change the field angle, so I don't have to look directly at the target. I can rotate the eye or the target. Down here I can select target type. So with it unchecked, I have a source target, like a point source, at 6 meters or 6,000 millimeters. If I checked object, I could pick an object target, which could be a user target, any image that you have that's a bitmap, or I can select an eye chart, an AI chart, or an EI chart. So here's where I put in my file name if I wanted to use that. I can scale it. I can even rotate the target itself, so the target will be upside down on the retina, so if I don't want it upside down, I can specify 180 degrees. Here's my retinal image window, so I specify how large a window I want to look at when that image projects to the retina. And then I have some other options here for focus. I've got an initial focus and a new best focus. Depending on what type of optics I've got set up in my eye, there will be some best focus for the retina. If I start going in my model and changing things, like putting in a lens or reshaping the cornea, I might create a new best focus. So the next time I go around and use the eye model, the retina would be at the old location. I may want to move the retina to that new best focus, or I may not. So I have that option. I can save history about the eye, so that means that I can look at rays that have scattered or rays that have hit certain objects. I can look at the rays in more detail in a ray history file. I can also insert a system that's totally independent of the eye, and it can be anything, some instrument or whatever I have that I want to integrate into the model. If the system that I'm inserting is retinal implant, I select that because that puts it inside the eye. I can opt whether or not to skip the default metrics that are generated with the eye, which are some various measurements of quality. And here are some options that I can use to set the display. So I can have 201 by 201 pixel display. I can average adjacent pixels in that display. When I draw my graphics of my eye, I can increase or decrease faceting. And then I've got a plotting factor for the rays. So I can control the amount of rays that appear on my graphics by increasing or decreasing the plotting factor. All right, so I'm going to keep things the way they are and just click OK. And then I get the next screen, which is a little more detail about the geometry of the eye. So here I've got an AZ accommodative lens power. Now this screen will be particular to the lens choice that I picked in the first screen. So here's my lens power. I can accommodate the eye. So I have a maximum of 5.5 diopters. And here I don't need accommodation, so I'm going to leave it unaccommodated. And I can place my anterior vertex in certain positions. Right now they're set up to follow the Arizona eye model, but I don't have to use those numbers. I can change them. So I've got things like lens diameter, thickness, pupil shift. I've got cornea thickness. I can rotate the anterior and posterior surfaces. I can change conic constants, corneal diameter. I can change how the iris is shaped. I've got a retinal thickness I can change. And then down here, I can look at my field that I generate when I send a source to the eye. I can look at that field in 3 dimensions. So if I leave it at 0, it won't go into that mode. But I can control a 3-dimensional point spread function through depth of focus. And then I can slice my way through that focus for resolution of that volume. All right, I'm going to click OK because I'm happy with what I have. And I generate a graphic of the eye. There's many graphics. So these are the basic metrics that I get. I also have some that are generated at the bottom of the command output window, where I have full width at half max information. I've got a 50% encircled energy. There's my initial and best focus. Well, let's look at some of these graphics. All right, we saw this plot already. Here's a retinal image 3D view in cross-section. So these 2 graphics are overlaying here in cross-section, and I've got a isometric view here. I've got a display. That's a point spread function, and I can look at that various ways. I can look at that in 3 dimensions as well. Cross-section graphic here. And then I have a retinal encircled energy as well. So these are some basic graphics, and the user can generate any type of ASAP graphics now because all that information about the eye is available, but these are just some standard ones that many people would be interested in. So that's the default AZ model. Another thing we can do with AHEM is image eye charts or any type of image through the eye model. So we're going to look at how to do that. We're going to look at a perfect eye model, and then we're going to put some aberrations on the eye and look at that, and then we'll correct some of those aberrations and look at an eye chart through the correction. So I'm going to start my eye model, and this time I'm going to load a saved file. So I'm going to click option 2, and that's my file name. Click OK. I'm just going to click default because I'm working with the settings file now. So now I have a few different things set up from our defaults. We're still using the AZ model. There's no correction on this eye. So now I'm selecting an object target type instead of a source. So I've got that box checked, and I'm using a lot of rays because I don't want to generate a clean image. And I've got eye chart and eye chart selected, number 2. And I've got a scale of 1, and I've rotated the target so that our eye chart is right side up when we look at it. We've got a larger retinal image window that I will want to look at. So it's 3 by 3 millimeters. And then I've increased my display pixels a little bit to 511. I'm going to do one adjacent averaging. Since I've got so many rays in my system now, I don't need to plot so many of them on the graphics, so I set that to 1. So click OK. And then there's my standard setup for the Arizona eye model. I'm not going to change anything. I'm going to click OK. The ray trace is completed, which took a few minutes, and these are our graphic results. We're looking at a long view of our target and our eye, which our eye is very small in this case, so we're going to zoom in. You can see that there's our eye. Now our isometric plots and cross-section don't make a lot of sense because we're cross-sectioning through an eye chart, so those are the profiles of the letters themselves. However, when we look at the display graphic, we get an eye chart. So this is through our perfect eye. So the next thing I'm going to do is load settings for an eye that has aberrations on it. All right, now I'm going to reload my settings for my aberrated eye. It's the name of my aberrated eye with astigmatism. So now many things look the same until I get to the next screen, or next couple of screens. And now I have a Zernike coefficient input window. So I've got some defocus and some oblique astigmatism placed on the corneal surface. I click OK. All right, our ray trace has completed. And now we're looking at our eye chart again, and we can see that the astigmatism that I put on the eye model is evident in the eye chart. So here is our perfect eye, and here is our astigmatic eye chart. So now I want to correct that. All right, now I am reloading the settings for my corrected eye, which I corrected using optimization. So I'm going to start my model. And I'm going to paste in the name. Okay. Okay, so here's my first splash screen. Not much has changed except now I'm going to do correction. So I've got a spectacle correction that I acquired. So I click OK. And my second screen, not much has changed here. Here's my Zernike deformation that's still on my cornea. Click OK. But now I get another input screen which asks me for spectacle correction data. So here's my sphere correction, my cylinder correction, and my axis correction. And then I've got vertex distance and some description about the size of the spectacle that I have on my eye. So I've got some semi-height and thickness to the lens, and then some width and roundness factors. So click OK. All right, so the ray trace has completed, and now we're looking at a graphic where the corrective lens has been inserted for me into the eye since I specified it, and the eye chart is transferring through into the eye. And then we can look at that graphic in the display, and this is the corrected image. It's not quite as good as the perfect image because it's only a second order correction in quarter diopter increments, but it's much better than the aberrated eye. So we can correct that further if we want to, but this is just a basic sphere and diopter correction here. So what we've done here is shown AHEM can trace any type of image target through the system, and we can add spectacle correction to that image. Lens cataract can be modeled using AHEM. So the image we're looking at right now is a few rays being traced into the eye and being scattered around by a cataractous volume within the eye. So let's load up a settings file of how we might set this up. I'll start AHEM, and I'm going to use the saved settings file. All right, so let's look at what we have here. I'm using scatter and reflections now, so I have this box checked. And I'm sticking with one wavelength for now. And I'm using an incoherent source. And for any kind of scattering, that's really what we need to use. I've got my AZI model, eye geometry. No correction, no ametropy or anything like that. I'm using a source target at 6 meters and filling the pupil with it. I have a small retinal window size of 0.05, or actually 0.1 by 0.1 millimeters. And everything else is pretty basic. I do a little averaging here. So I'm going to click OK. And now I get a splash screen that's relevant to splitting and scattering. So I have my split Monte Carlo option on, which can save ray trace time. And I have various options here for setting splitter and scatter levels for the various elements of the eye. So I can have a global scatter level. So if I have any other types of instruments or optics other than the eye, that generally applies to those optics. And then a sub-level of that, I can change the various scatter and split levels on the different eye elements. So I've got cornea split and scatter, aqueous split and scatter, lens split and scatter level. So here I'm concerned with scatter in the lens and not anything else really. So that's where I have my numbers set, is particular to the lens. If I have volumetric scatter, I want to have a high scatter level for that. Generally 100 is enough. I've got 1,000. Cataract mean free path is related to density. All right, so I've got 3.85 millimeters in this case, and then a particle radius. So these are some numbers that are found in the literature in modeling nuclear cataract. I have an option to plot a cataract function, so I might click that. And so I've got vitreous scatter and split. I can also have retinal reflectance as well. So if I send light into the eye, I can have it reflect out of the eye and do anything else with it that I want to afterwards. So I'm going to click OK, and then I get my particular geometry set up here. This is the AZ lens model once again. I'm going to leave everything set the way it is, and I click OK, and there's my lens volume scatter graphic. All right, so I get a graphic here where I show some rays scattering, but I'm really interested more in the retinal PSF. So this is it here, and if we look at the numbers here as far as maximums go, what I've done is I've set various levels of scatter attenuation. So my particle size is staying the same, but I'm increasing the density of the particle size in the eye lens. So I've got 5 different levels of cataract set up, much like you would for nuclear cataract. And if I step through the different levels, this is the first level, and the second level, you'll see the numbers change up here as far as maximums, and over here, intensity of that point spread function. So as I increase the density, you'll see these numbers go down, and relative to the density of the cataract. And I keep going down, and there's a little more scatter out here in the periphery as well. It's gone down to 2.1, and even farther here, 9.2 e to the 4th instead of the 5th. And if I enhance this, I can see a little more of that scatter on the outside. So that's how light scatter behaves when you're keeping the particle size the same and increasing the concentration. I can also go in there and change the particle size as well as the concentration at once. So I can do either or both of those changes in scattering to model cataract. We're going to use the eye model to model an intraocular lens now. And then we're also going to visualize the appearance of the intraocular lens from the outside, from the cornea. So let's look at that intraocular lens, which is inserted into the eye first. So I'm going to remove some surfaces here. I'm going to remove the sclera and the retina. And here's my intraocular lens in the green. And we see haptics around that lens. and this is the front of the eye. So we're going to look at the cornea and see if there's any reflections by passing light into the eye and looking at it from the outside. So this is lid appearance modeling. So I'm going to load my settings file from my intraocular lens. So here I've got some settings. Going to use setting number 2 for intraocular lens for my eye model. So here's my number 2, and most of the other geometry is set up similar to the default mode. I'm using a source target. It's unchecked, filling the pupil, and so I click OK. And now I have some particular settings for an IOL in my next input. I can shift the iris if I wish, and then various other geometry associated with the eye. Click OK. Now it's asking me for some more detailed information about the intraocular lens. So I can generate an IOL from some other CAD file and call it here. So I've got a lens called IOL1, and I can also scale that lens. So if it's a small lens and I want to make it larger, I can put a scaling on that, and I did that here, 1.7. I can stretch it on the z-axis. Here I'm just keeping it the same. I can position its anterior vertex, and I can do various other rotations or shift on that intraocular lens as well. I click OK, and it's running, draws the graphic. All right, so my ray trace is complete, and we're looking at some graphics. I did a coherent trace through this system, so we see the coherent graphics, and there's my trace and plot. Here's my isometric plot and my cross sections and my other graph cross sections. Here's my retinal and circled energy. So this is a pretty good IOL, much like a real eye. So in order to do the lid appearance model, I need to take another step with AHEM. I need to export the geometry as a system. So I do that with a system 2 command, and then the name of the file that I want. And now I'm exporting all this geometry and all the media and all the settings so I can process this externally. So I've done that. So the next thing I want to do is load my system file for generating my lid appearance modeling. Where are you? Here it is. All right, so what's going on here now is I've got another ASAP file that employs that system by recalling it. So I've created an entirely new system where I'm going to remove the iris and then do the lid appearance modeling. So here's my system from. I bring that back in. I do a numbers name command to find out what my iris is called, and that's what it is, iris.1. So I consider everything in my system except that iris. I create a source, and I trace that through the system, and I select the rays that miss or that leave the eye, or that are leaving the cornea, and I dump that to a reflection distribution file. So then I go into the BRO 3D viewer, and I have my geometry of the eye, which I'm going to zoom into a little bit. And I go here and I say I want to set up my spots analysis preferences. And I pick that file that I just generated up here. I'm going to include all my rays, and there's some various other settings for the BRO 3D viewer for lid appearance modeling. And I say OK, and then I perform a spots analysis. And behind the scenes, that's been put on the clipboard, so I can take that information and go over to PowerPoint and paste that in. And there it is. So let me make this a little bit smaller. So paste that into my PowerPoint. So I have a representation of the orientation of the eyeball here. And then I see a graphic of the lid appearance. And if I make that larger again, let's Go back to 100. Let's look at that a little bit. We can see the reflection of the center of the IOL on the front of the cornea. We can also see some reflection of the haptics that were surrounding that intraocular lens. So this is an application of AHEM to investigate reflections off an intraocular lens when the iris has been removed from the eye. We're now going to use the eye model to look at aberrations through a field or through depth. So here we're looking at the aberration coma that we've put on the cornea of the eye. So we're looking at the image plane right here. So some aberration has been put on the cornea. Light has traveled into the eye. Here's a cross section of that coma and an isometric view. And the display once again. So in order to do this, I go and load my coma aberration. So I have a saved settings file. Say OK. All right, so I've got a coherent mode as well now, so I have that box checked. I've got an anterior corneal Zernica pupil diameter of 5.7, which is the same as the pupil of the iris. So I'm going to deform over that cornea with some coma. So I click OK, and I get another screen related to my AZ basic geometry, my AZ lens model. Here I've got my 3D PSF and number of slices through focus set. So now that I have numbers here, that will invoke that feature. So I'm going to look through depth of 0.2 millimeters, and then I'm going to slice up that depth into a volume and look at the field of the light as it travels into the retina. So click OK. And then I get my Zernicke deformation screen, and I've got just 0.01 microns of Zernicke coma on there. So I click OK, and the trace begins. So now we have our volume of a field of that coma. We're looking at depth of field, or depth of focus, if you will, to the retina. And I can look at various planes, and when I click on them, I see their location and what axis they're on and what axis they're relevant to. I can hide different planes, and I'm going to hide a few here so I can look at that aberration a little more. I can also move the planes through that depth using the 8 and 9 keys on my keypad. So I can move through focus and see how that aberration changes. Let me hide this one. I can do that with any of these planes. If I just click on them, I can move them in the respective direction. So we see that chromatic aberration maintained through the field. Here is the aberration directly on the best focus of the retina. We're now going to use the eye model to create a gradient index lens inside the eye. So I'm going to zoom in, and we see that the eye lens has a multi-layered structure just like the real eye. So we're going to start AHEM. And I'm going to load a previous settings file. So now we have the grin lens selected, number 1, and most of the other parameters are similar to the default eye model. So we're just inserting the gradient index lens into the system. So I click OK, and I've got my next splash screen that's more dedicated to the gradient index lens geometry settings. So I've got an unaccommodated thickness and an accommodated thickness. So what we can use this for is if we want to put accommodation on the lens, or if we want to simulate aging and the thickness associated with aging. We can also globally adjust the gradient index profile of that lens by adding or subtracting any amount we want to the individual layers. And we can show a table of those layers and adjust them further independently. So I have that box checked. And then the rest of this data is relevant to the geometry of the rest of the eye. Click OK. And I've got another new splash screen that shows the different layers and their different indexes. So the innermost layer is the embryonic nucleus, which would be this green layer. And as I go outward, I've got various changes in index. So this is my gradient index lens profile for the various 13 layers of this lens. So we've got an embryonic nucleus, a fetal nucleus, a juvenile nucleus, an adult nucleus, and a cortex. So as you age, you acquire these various nuclei due to the layering of the lens fibers onto the lens. I'll click OK. So we're creating our eye lens and our eye geometry, and we've got our tracing going on. So here we're looking at a point spread function of the gradient index lens eye model, and we have a retinal window of 1 by 1 millimeters. So this is a retinal image, and we've got a nice compact point spread function. The spherical aberration of the eye is much reduced by using a gradient index lens. That's an advantage to that system that we have in our eye. We can look at our graphic again here in 3 dimensions, and I can take away some parts of the eye so we can look at that eye lens in more detail. So I'm hiding the sclera, now I'm hiding the retina. And so here we see that onion-shaped eye lens. I'm going to zoom in a little bit here. And I'm also going to remove the cornea for viewing and some of these in the iris. So we can see we have 13 layers, and I can hide them, and you can see how the lens is structured as I hide the various layers. They're all on top of each other with different indexes. I can also assign different scatter properties to the individual layers as well. So if I want to simulate cortical cataract, I can put scatter models in the cortex. If I want to simulate nuclear cataract, I can put scatter models on the various parts of the nuclei. So I can simulate just about anything with the eye lens in a multi-layered gradient index application. Right, now I'm going to use the eye model to simulate a retinal implant. So we're looking at a graphic here of the eye model and also a corrective lens in front of it, because if we put an implant in the eye, let me zoom in on it, you can see the retinal implant, and let me hide the sclera in the retina. You can see that it sits inside there and has some thickness to it. So that's why we need to have a correction in front of the eye. So let's go ahead and use AHEM to set this up. I've got my bionic retina settings. Alright, so here's my first splash screen, and I've got a basic setup similar to the default model. However, when I get down to the bottom, I have an option to insert system, and a bionic retina is a system. But now it asks me, is a system a retinal implant? In this case it is, so I have that checked. I increased my faceting a bit so I could see the curvature a little better, and I click OK. And here's my AZ lens settings, so I have geometry for the eye set up for the AZ model. Click OK. And here are some information that's asked for, particular to the inserted system. So here I've got a file name for a bionic retina. So I can create that file either in ASAP or in some CAD application. Then I can bring it in to my system. So I can scale it in X and Y. I can stretch it in Z. I can move the vertex on the Z-axis of the anterior surface. I can shift in X and Y, and I can rotate it. Click OK. And from what I was describing before, we need to correct for the eye because we put a surface on the retina which moves that image to a different location. So I put 2.75 diopters to correct that. And I used optimization to find that number. So I insert some sphere. So I'm going to put power on the eye from the corrective lens. Click OK. And it begins to run its trace. You see the geometry drawn. There's my correcting lens. And I get a point spread function that's nice and tight. It looks much like the default model's point spread function and also cross-section data. So there's my point spread function. And let's look at our geometry again here. So we've got a bionic retina inside the eye, and we're imaging on top of it. In this example, we're going to use optimization to correct an eye model. Here we have an eye with axial myopia, meaning that the rays are coming to focus before the retina. So if I zoom in here, we can see that the best point of focus is before the retina, which is here. So we would like our retina to be there, but it isn't. So we need to correct so we can push these rays back onto the retina. But how do we figure out how much to correct? Well, we can use optimization to do that. So to use optimization with AHEM, we need to go to the settings file of what we have generated in our system. So each time we run an eye model, a settings file is generated. So we open up that settings file. It contains all the variables that are inside the model. So if we know what variable we want to optimize for, we can select it from this file. Now there's a certain procedure that we need to do to use the optimization. So we can go up into our templates file and select AHEM Optimize Top. And so what it did was it inserted some code at the top here, the system new reset, units millimeter, and then insert settings file here. So here's my settings file, and I go down to the bottom. I click on AHEM Optimize Bottom, and then it inserts the bottom. So I need to have my settings file in between the red lines of the top and bottom of these two templates. This allows me to use the optimization state of AHEM. Now I want to optimize. I go into the editor and I say optimize script. So now I want to find the design variables to optimize for. Well, if I want to push the rays that are not focusing on the retina to the retina, I need to put some sphere on those rays. So I'm going to use sphere for design variable. So I'm going to search for that variable and sphere 1 for sphere I1. And all these variables are listed within AHEM's library. So I'm going to find sphere 1. There it is. So I'm going to select it. And I'm going to right click on there and I'm saying define design variable. So its original number is 0. And now the optimization is going to figure out what the best power to put on the correction lens will be. Now my design objectives, I need something to design to. So there are various metrics that AHEM generates automatically, and full width, half maximum, and a 50% encircled energy are two good design objective metrics. So I want a compact point spread function, and those two metrics describe the compactness of a point spread function. So I'm going to search for those metrics, or for one of them at least. Let's see, I've got full width half max of I1. So I'm going to look for that. There it is. So I'm going to select that in a similar way. I right click on it. So there's my design objective. So this is a very simple setup. And then when I'm done, I just say start optimization, and the optimization process continues. So the ASAP optimization finished processing, and it gave me a number for the sphere. So right now we're looking at a graphic of the ray trace after I've put sphere on a corrected lens. So let's see how that looks when we run it. Alright, so I've got my eye set up basically the way it was before, where I had 2 diopters of ametropia on it, and I was getting that axial myopia where the rays were focusing before the retina. So then I needed to correct it. So now I have a choice to correct that. So I have selection 1 for spectacles, and I got the data for the spectacle correction from the optimization that I just performed. So everything else here is the same, except now I've got input for spectacle lens sphere. So here I've got minus 1.65, and I got that from the optimization. So I plug it in here, and I just say OK, and it generates the ray trace and the corrected eye model. So look at some of these views. There's our point spread function, nice and tight and compact. You can look at the plot. So here's it's a negative lens, so it's minus 1.65 power to make that nice compact point spread function pushed onto the retina now. So we can look at it. Circled energy looks good, and there's a cross section of our PSF. So in summary, we took an aberrated eye with axial myopia and ran ASAP's optimization process using sphere of a corrective lens as a design variable, and then we used a design objective full width of half max, and we tried to drive that to 0 because we want this half max full width to be as minimal as possible. And we ran that through the optimization, and it gave me a number of minus 1.65 diopters to put onto my corrective lens. Here we use the eye model to simulate 2 eyes. In this graphic, we have 2 eyes looking at a target at 1 meter, and they have some vergence or rotation to the eyes while they look at this point. So let's kind of zoom in there a little bit. You see we have rays from that source target going into both eyes. There's another graphic, or a top view. So anything we can do in AHEM with 1 eye, we can do with 2 eyes, and we can also assess the vergence and what happens to the image from the vergence when we use binocular modeling. So let's run through AHEM in a binocular mode. I'll load my settings file. And here's my first basic setup screen. So now we have 2 eyes that we're using, and I'm using an incoherent mode, 1 wavelength, and I'm going to stick with the AZ basic model. So both eyes will have this basic eye model. So these are going to be emetropic eyes. There's no ametropia on any of the eyes. I've got a pupil size of 7.5 millimeters, and I've set my target distance to 1 meter. So the eyes are not looking at infinity now, they're looking at 1 meter. So they're going to need to accommodate the image for 1 meter as well. So we'll see that in a second. So here's my retinal image window. I've got faceting of 5 and some typical setup features. Click OK. Now I get a new window of binocular settings, and I get a setting for interpupillary distance. So that's the separation distance between the center of the pupil of both eyes. Different people have their eyes separated different distances, so 55 is a fairly average number. Here we see the horizontal vergence for both eyes. We see I1, I2 now specifying each new parameter that we have. So we've got some rotation to the eye now. Here it's just over 1.5 degrees. One eye is turning inward, the other one well, they're both turning inward. So one is positive and one is negative. So we see both eyes and their parameters set up next to each other for comparison. So the next screen shows the AZ lens geometry because that's the lens choice that I chose for both eyes. And now we're seeing it particular for eye 1 because they don't have to be the same for each eye. We can set the models independently of each other. But this is the basic geometry for the AZ eye model for eye 1. And notice that I have put one diopter of accommodative power on the eye lens. I've moved my target to 1 meter from infinity, so now I need to accommodate 1 diopter. The inverse of 1 meter is 1 diopter of divergence. So now we have eye 2, and we have similar eye geometry settings. I also put a diopter of accommodation on that lens, and this is my basic geometry settings for eye 2 now. Click OK, and draw my geometry, and rays are being traced. So I get some graphics, some additional graphics when I use 2 eyes. So I get a point spread function, and you can see that there's a certain amount of shift off the center of the retinal window that I selected because the eye has rotated 1.5 degrees. So we actually see that showing up here in the retinal image window. And we also see it for eye 2. It's just gone the other way because there's eye 2 is rotating inward and eye 1 is rotating inward. So you'll see them go outward. So we have a retinal image for eye 1. We have encircled energy for eye 1. And we also have overlain retinal PSFs. So these eyes were basically the same as far as aberrations and being emmetropic and accommodated 1 diopter. So their point spread functions are very similar. So here's the eye 2 retinal image. So I can look at each one independently or overlain. So there's eye 2 retinal image and eye 2 encircled energy. And once again, here's our 3D view. And we can look at our eyes and rotate them around and see it this way. So in summary, any operation that we use AHEM for, we can do it for 2 eyes as well. We're now going to use the eye model to simulate contact lens. So here we've got an aberrated eye, and we'll look at a retinal image. And there's a lot of aberrations here. So we're going to put a contact lens on this eye to correct it. So we're going to load up AHEM. I've got a settings file with contact lens. And I go to AHEM and my basic setup. So now when I go to correction, I select 2 for contact lens or lenses if I had 2 eyes. And the rest of my setup is fairly standard. And I'm also using a coherent application here. So I've got a retinal window here, the same size as the retinal window we saw here. And I've done some correction with the toric lens. So I click OK. And my basic eye geometry is shown for the AZ eye model. Click OK again. I don't need to change anything here. And this was the aberration on the cornea that created this retinal image here, this aberrated eye. I've got basically no point spread function because I put this aberration on this eye. So I click OK, and now I get prompted for contact lens file name. So you can create a contact lens in some other CAD application, or you could create it within ASAP. So I created a contact lens within ASAP. Have a scaling factor that I can use. I can make it larger or smaller. I can reposition the anterior vertex. So I backed it off the front of the cornea in this case because the anterior corneal surface is Z0 for the entire system. So I have to go negative to back it off the cornea just a little bit. So I click OK, and here's just some basic sphere that I've put on this particular contact lens. It's not optimized, but I've just put a basic quick correction on this eye. I can match the back optic zone radius to the cornea radius that I have on the eye, so I don't have to figure out that number if I don't know it, because the contact lens, if it's a soft contact lens, will just fit flat on top of a cornea. So I'm going to click OK. And it's not the greatest correction, but it demonstrates the use of a contact lens that I created in CAD. Let's look at some of these views. So here was my original horrible image of the point spread function. With my contact lens correction, I was able to make that pretty compact for a point spread function. Still has some issues to deal with here with some astigmatism, and I could get that a little tighter, but it's not a terrible PSF for the correction that I made here. So this is my contact lens. Right here we can zoom in on it. It's a toric contact lens. I can zoom in a little more here. You can see this layer on top of the cornea. It's a different color than the cornea. So that's contact lenses in AHEM. You can either import your own from CAD or generate one in ASAP to load into AHEM, and then you can reposition it with the splash screens. In this example, we're going to model two eyes in a system where the eyes are looking at an eye chart. One eye will be different from the other, so we will have two distinct retinal images. So here's our two eyes looking at an eye chart. So let's load AHEM and see how we would do this. So I have a settings file, and I'm going to load. Click OK. Here's my basic setup, and I've got two eyes selected. I'm going to use the AZ eye model for both eyes. So my setup here is for a target. I'm going to use an object, so I've got this box checked. And my source target grid rays will be 121 by 121. I've got an eye chart, eye chart selected for a target. If I wanted to, I could use any image that I have. I'm going to rotate 180 degrees to look at it so that the inversion caused by the eyes will be upright. And I've got a retinal image window set and some display pixel settings and some other standard settings. I click OK. And now I get prompted for information about both eyes. I've got a standard interpupillary distance of 55 millimeters, some vergence, and I've put 5 diopters of axial ametropia on one eye. So I've made one eye longer, giving it myopia. So that one will have a blurred retinal image compared to the other eye. So the rest of the settings I kept the same, and I click OK. And I've also got one diopter of accommodation on both eyes' lenses. So the target is at 1 meter, so I'm going to accommodate both eyes 1 diopter. Yet one eye is going to be longer because I put 5 diopters of ametropia on it previously. So all the other settings I'll leave alone, and I'll click OK. And here's my second eye. And here's just the 1 diopter of accommodation, just like eye 1. I click OK. And begin to trace our rays. So we see rays going to both eyes. And we're looking at an overhead view of the eye chart here. And rays starting from it and going towards the eyes. You can zoom in here and see those rays entering our eyeballs. All right, so we've got our data generated, and I can look at some of the information here. Let's take a look at our display. And we've got eye 2 on the left and eye 1 on the right. So notice eye 1 was the eye that I did not put ametropia on. So this is the correct eye or emetropic eye. And then the blurred eye or the myopic eye where I lengthen the retina or lengthen the axial length, is the blurred image. So if I was inclined, I could also free fuse these images, and I could see the three-dimensional stereopsis associated with these images. I can look at each image individually. So here is the clean corrected image from the emmetropic eye, and here's eye 2. You see it's blurred from the myopia that I induced from putting 5 diopters of axial length from the emmetropia. This is just another way to view images. I can change the palette, so I can use a gray scale or a color scale. I can have various ways of looking at my images. Down here in the chart viewer, the cross sections don't make much sense because we're taking a cross section through letters of the alphabet, and neither does the retinal encircled energy because we're looking at a wide field now. However, if we look at the overlapped retinal images, we can see that there's much more energy in the corrected eye, than which is the red eye 1, the solid series, and eye 2 is the dashed green line, which has much less energy in it. So once again, we can model 2 eyes with independent optics and independent aberrations from each other and create images that are respective to both eyes, and we can free fuse them if we wish.